Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So as you know, within this module we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module, we are now going to start with a new topic, that is the fifth topic of time sharing, right? So within this topic, we are going to study about time sharing. We have already talked about time sharing in the previous module also. So basically the problem that we are trying to solve here is that in any computer system, the number of CPUs that are there, that is limited, right? And the number of processes that have to be executed on these CPUs is way more than the number of CPUs. So the problem is we have lesser CPUs and more processes, right? And in order to solve this problem, in order to run more number of processes on lesser number of CPUs, we have this concept of time sharing, right? So we are going to talk about time sharing in more detail in this video, right? And we are also, throughout this topic, we are also going to talk about another concept, that is CPU scheduling. So CPU scheduling is basically the mechanism that is used to implement the concept of time sharing. CPU scheduling is basically how we allocate the CPU to multiple processes, right? So we are going to talk about what is CPU scheduling, how it is done, what are the mechanisms that are required to implement CPU scheduling, when it is done, who does it. We are going to all answer all of these questions, right? So by the end of this topic, you will have a good idea of how multiple processes share the CPU time and how the operating system implements this overall mechanism, right? So without further ado, let's get started. So let us start this video by recalling what is the concept of time sharing, right? So to explain time sharing, I have an example for you, right? If you see this diagram, so basically we have a computer system which has some CPUs, right? And as we know, the number of processes that would be executed is way more than the number of CPUs, right? So let's say the number of CPUs is n and the number of processes is m. So m is greater than n. So let us take a simpler case, that is, let's take the case when we only have one CPU, right? And we have n processes, let's say, right? So this is the case that you can see in this picture. We have a computer system which has only one CPU, right? Right. And we have n processes that we want to execute on this CPU. So how can we do that? We know that at any given point in time, the CPU can only execute one process, right? So this is the constraint from the hardware. At any given point in time, the CPU cannot execute more than one processes, right? Over a period of time, obviously it can switch between different processes, right, and execute multiple processes, but at any given time instant, there will be only one process running on the CPU, right? So as we know, so to solve this problem, we have this concept of time sharing. So what we do here is that the resource that is in concern, that is limited resource that we have, is the CPU time, right? And the entities that want to share this resource are the processes. So basically we have a resource that is in scarcity, that is CPU time, and we have several entities, that is the processes, that want to use this limited resource. So whenever you have any such scenario, when the resource is limited and the entities that want to use the resource are more, you have to share the resource, that, right? So the answer to this problem is that we have to share the CPU time. That is why this concept is named as time sharing. So the way we do this, basically the time sharing is implemented by the operating system. So the way operating system deals with this situation is that it will switch this CPU between these multiple processes, right? It will allow any given process to run for a limited amount of time, right? And after that brief period of time has expired, the operating system will take control of the CPU from that given process and give the CPU to some other process, right? And it will continue to do so. It will continue to switch the control of the CPU among different processes. So what will happen in this way? Basically, all of the processes will get to execute on the CPU and make progress, right? So even if we have limited number of CPUs, we can execute multiple processes by sharing the CPU time between multiple processes, right? So this is the concept of time sharing that is implemented by the operating system. So this basically allows us to run more number of programs on systems with lesser number of CPUs, right? This is the fundamental problem that we are trying to solve, to run more programs on limited number of CPUs, right? So this is the basic idea of time sharing. Let's talk about, let's see time sharing in more detail and see some other points as well. So the first thing that I want to talk about is, let's first understand the difference between time sharing and parallelism, right? So what happens when we have basically multiple processes time sharing the CPU versus multiple processes running in parallel, right? So as you can see in this diagram, on the left we have processes time sharing the CPU. On the right we have processes running in parallel. So on the left you can see there is a single CPU and there are two processes P1 and P2. And you can see the CPU time. This is from left to right as we go. This is the CPU time. It is being shared among processes P1 and P2, right? So P1 runs for some time, then P2 runs, then P1 runs, right? In this way, we are switching between P1 and P2 and sharing the CPU time. Whereas if you look on the right side, we have multiple resources, right? We have two CPUs instead of one. We have two CPUs, and we have, just a hypothetical example, we have two processes, right? So here you can see P1 and P2. So P1 is running on CPU 1 and P2 is running on CPU 2, right? Both of them are running in parallel at the same time. There is no sharing. If you look at CPU 1, it is dedicated to process 1, right? Or we can say process 1 is exclusively using CPU 1. There is no sharing of CPU 1, right? In the same way, there is no sharing of CPU 2. So you can see the difference between time sharing and parallelism. The first point is that in the first case, as the name suggests, right, here the resource will be shared. Here the CPU, you can see, is shared between different processes P1 and P2. There can be more processes. Whereas in case of parallelism, when we have processes running in parallel, here the resource, the CPU time, is dedicated to a single process. P1 is, for the entire time duration, the CPU 1 is being used by P1. It is not being shared. In the same way, CPU 2 is also not being shared. So first difference between time sharing and parallelism is that in the first case there is sharing of the resource of CPU time, whereas in case of parallelism there is no sharing, right? And another thing is that in case of time sharing, right, basically, let's say, if you see on the left side, at any given point in time there is only one process running, right? You can say that P1 and P2 are using the CPU, or two processes are running on this CPU, but they are running not like at the same time. What I want to say is that if you take any time instant, right, on this horizontal axis, if you take any time instant, at any time instant, only one process is executing, right? Whereas if you consider this second case, if you take any time instant, then in this example, there are two processes executing at the same time, right? So this is a crucial difference. In case of time sharing, although multiple processes are running on the CPU, but never at the same time, right? P1 and P2 are sharing the CPU, but not at the same time. At any given point in time, we know that there is a constraint in the hardware that the CPU can only execute a single process. That is why, in the first case, there is always a single process, only exactly a single process running on the CPU. Whereas when we have multiple resources, we can have the liberty, right? Here you can see at any given point in time, in this example, two processes are running. So this is another crucial difference between time sharing and parallelism, that is how many processes can run at the same time. The first one is the first difference was about the sharing of resources. The second difference was about how many processes can run at any given point in time. So let us now discuss the pros and cons of time sharing. So on the left side, I have an example where the CPU is being time shared between two processes P1 and P2. And on the right, we have a case where the CPU is not being time shared. So let me explain these examples also. So here, as you can see, the CPU is being frequently switched between P1 and P2. For some amount of time, P1 is running, then operating system gives the control of the CPU to P2, then back to P1, then back to P2. And in this way, it is switching the control of CPU to and fro between P1 and P2. So this is the case when we have time sharing. On the right side, in this case, what we are doing, we are allowing the process to run until it completes. We are not stopping it in between and time sharing the CPU. So P1 starts running and it will run until it ends. It will not, like, the control of the CPU will not be taken away from the process P1 in between, right? Similarly, for process P2, it is allowed to run until it completes. So we're not stopping the process in between. We are letting it run until it completes. So we're not switching the control of CPU frequently. So this is not time sharing, right? So what are the pros and cons of these two cases? The con, or basically the disadvantage of time sharing, is that programs will run slower on a time shared system. So if you see, the length of process P1 is the same in both the examples. I have made the example in such a way that both P1 and P2, they have identical length, basically running time in both the cases. But since in first case we are like implementing the time sharing mechanism, the same process P1 takes a longer time to finish, right? If you see, this is the starting duration, and the P1 completes here. This is taking a longer time as compared to the case when we are allowing the P1 to run without any switching in between. This is the second case when we are not time sharing the CPU. So once the CPU is allocated to P1, it is dedicated to P1. So this is, you can see it finishes much earlier as in the case when we have a time shared system. And the same is true for P2, right? P2 here you can see takes a shorter duration, whereas here it starts somewhat earlier and ends in the ends here. So you can see in the left side, the time, the whole duration that is taken for completing a process is more than on the right side. So this is the disadvantage of a time shared system, is that processes will run slower because they are sharing the CPU, right? We do not allow the CPU to be dedicated to any one single process. We are sharing the CPU, so it will take more time to finish the processes. So this is the disadvantage. So why do we do time sharing? What is the advantage? Advantage is that in the first case, the programs are more responsive, right? So if you see here, P1 is run for some time, but it does not, the operating system does not allow the control of the CPU to be with P1 forever, right? So it takes away the control of the CPU from P1 and gives it to P2. So you can see P2 starts earlier in this case. Both of the processes get a chance to execute the CPU. This is more responsive system. In the second case, P2 does not start until P1 finishes, right? You can see it starts much later. So although we can say for process P1 this is responsive, the first process, but for the other processes that are waiting in the queue, this mechanism or this policy is not responsive. The other processes will have to wait for a longer duration, right? So you can see, if you're waiting for process P2, if you're using process P2 in this system, the wait time is much more. In this case, since we are sharing the CPU, P2 starts much earlier, right? And the system is more responsive. Both of the processes get to use the CPU and make progress. You can see in the left side, both of the processes are making progress, right? Although the entire duration will be longer, that is what we discussed, right? The programs will, at an overall level, the programs will run slower, but you can see that since all of the processes get to use the CPU in case of a time sharing system, the system as an overall is more responsive for all the processes. Whereas if you don't use the time sharing, right, first for one process it will be fine, the first process it will be fine, but for all the other processes the waiting time will be very high, the system is not responsive. So this is the pro and con of using the time sharing system. So the next point about time sharing, it's a very important one, is that time sharing is transparent to the programmer. So what does it mean when we say time sharing is transparent? So basically, uh, when a program or a process is executed on a system where time sharing is being followed versus when it is being executed on a system where time sharing is not followed, the results will be the same, right? The overall behavior, the functional correctness, both of them will be the same. So in this way, the programmer does not need to worry or even be aware whether the processes are being executed on a system where time sharing is followed or not. So what I want to say here is that if you look at this diagram, right, in this previous slide, in the left part, the P1 and P2 are time sharing the CPU, whereas on the right part, P1 and P2 are running uh, till they complete, right? So here P1 is started and then it is allowed to run until it ends. Same is the case for P2. So here important thing is that process P1 and P2, when they are running, they are not stopped, right? So this is the simple case. But when we are time sharing the CPU between multiple processes, you can see we are running P1, we are starting P1, and after some time we are stopping it. We are pausing this process P1, then letting P2 run. We are then again pausing process P2, then resuming P1. So here the difference between these two cases is that here we are pausing and resuming the process, and this has to be done carefully. So in no way time sharing should not introduce any kind of error. You're pausing a process, right? When a process is executing, a whole bunch of things is going on. The contents of the CPU registers is changing, memory is changing, the process interacts with the IO devices. So it's a whole activity that is going on, and when you halt that activity, and when you talk about resuming that activity, when the process is resumed, it has to be done exactly at the same point where it had been halted, right? Everything should be the same. In no way pausing and resuming the process should introduce any side effects, right? Here, when we are not doing time sharing, things are simple and safe, right? We are not doing any thing special here. But when you're pausing and resuming, you have to be careful. So this is something which the operating system has to ensure, that when it is introducing this concept or implementing this concept of time sharing, in no way the overall correctness or the behavior of the process should be compromised, right? The only thing that will change is that the processes will take more time to complete, right? We discussed about the cons and pros of time sharing. When a time sharing system is implemented, the only things that basically will happen is that at an individual level, each process will take more time to complete, and on the upside they will be more responsive. But the bottom line is that in no way any kind of correctness or behavior should be compromised. Whatever is the behavior of process in a timeshare system, it should exactly match the one in the case where we do not have a timeshare system, where we are letting it run till completion, right? This is a very important point. So how does the operating system ensure this? How does it make sure that when we are pausing and resuming the process in this way, this execution, the result of this execution, the behavior of this execution should exactly match this one, right? Only it will take more time, that is fine, but overall correctness should not be compromised. Overall result should be the same, right? So to do this, the operating system has to be careful. When it is pausing the process at any instruction X, whatever is the state of the system, whatever is the state of the registers, the memory, overall hardware, whatever was happening, everything, every important thing has to be saved properly, right? So that when this process is resumed at a later point in time, all of that can be restored, and to this in the same way, to restore to whatever was there at instruction X. So when process P1 is stopped, some other process will be given the control of the CPU, and it will change the CPU registers, it will change the contents of the memory, right? So the system state will change. But when process P1 has to be resumed, the state should be exactly as it was at instruction X, and then process has to be resumed at instruction X plus 1. Only when these things are ensured, we can be sure that these two executions will result in the same results and behavior. So this pausing and resuming part has to be done by the operating system very carefully. So again, let's say it is paused at instruction Y, it will be resumed at instruction Y plus 1 with the same state, right? So even if we execute these an instruction on a system where we do not have any time sharing system, the results, the behavior should be the same, right? So that is only when that time sharing will be transparent to the programmer. The programmer as such should not get affected in any way. Whatever results they were expecting, they should get that result, right? So this is something the operating system has to ensure. When implementing a time sharing system, the pausing and resuming of the process should be carefully done, and the result should be the same, so that the programmer gets the same result whether its processes are executed on a time share system or on a system where time sharing is not being followed, right? So this transparency has to be maintained by the operating system, right? So the next point about time sharing is that it creates an illusion of a private CPU for each process. So what does this mean? So as you can see in this example, we have a single CPU, right? This is the hardware CPU. And we have multiple processes that want to execute on this CPU. So the operating system implements the time sharing mechanism where each of these processes are sharing the CPU. And in this process, what happens is that each of this process is given an illusion that they have a private CPU of their own. Basically, since all of the processes are sharing the CPU, they are able to make progress. They are all able to execute their instructions. So since all of the processes are making progress, although at a slower rate, right? It feels that all of these processes are executing simultaneously, but obviously that is not the case. At any given point in time, we only have one process on the CPU, but by switching the CPU between these processes frequently, all of these processes can make progress, and that is why it feels that there are n CPUs in the system. It is obviously just an illusion. We only have one hardware CPU, but since using this just one hardware CPU, all of these processes are able to make progress, they get this illusion that they have a private CPU of their own. So let us take a closer look at how this is happening. The first thing is that when these processes are executing on the CPU, the operating system is switching the CPU between these processes at a very high rate, right? It is not allowing any process to run for a very significant amount of time. it is switching at a very high rate, right? So within a given second, it is possible that hundreds of processes can run. Basically, each process getting, like, let's say, I'm just assuming that 10 milliseconds to run, right? The next thing, the first thing is that you have to understand that the operating system is switching the control of the CPU very frequently, right? The next thing is that uh, even within a few milliseconds that each process get, since the modern CPU is very fast, it can execute millions of instructions, right? A modern CPU can execute millions and billions of instructions in 1 second, right? So even if a process is given few milliseconds, hundreds and thousands of instructions can be executed within that time frame, right? If you see, within this time scale, you can see each process is getting only a small time slice. If we look closely at any single time slice, even this few micro milliseconds, let's say, is enough, because the modern processor is very fast. As I said, it can execute millions and billions of instructions in 1 second. So even this few milliseconds is enough to execute thousands of instructions. So the process will make progress, and all of the processes will make progress, right? We are sharing the CPU time between all of the processes very frequently, and the modern processor is fast. Combining these two facts, the consequence is that all of the processes are making progress, right? That is why it feels that all of the processes are executing simultaneously. Obviously, they are not executing simultaneously. There is a high frequent, we can say, context switching going on, but it creates an illusion. It creates an illusion that all of the processes are making progress. The illusion is that all of the processes are executing at the same time. That is why each process in this time sharing scenario feels that they have a private CPU of their own. Obviously, that is not the case. We only have a single hard physical CPU. In this example, we only have a single hardware CPU, but nonetheless, since the operating system is time sharing is this CPU among these processes, each of them kind of feels that since it's making progress, right? Each of the processes is making progress because operating system is switching the control of the CPU at a very high rate, and the CPU is fast. So each of these processes is making progress. Thus, each process gets this illusion that they have a private CPU of their own. Obviously, it's just an illusion, right? And this illusion is called a virtualization of CPU, right? Basically, what the operating system has done, it has taken a single hardware resource, single physical resource, and by implementing this time sharing mechanism, it has transformed this single physical resource into many virtual resources, right? There are, we can say, n virtual CPUs in the system. It is a concept, it's a virtual concept, right? Basically, since each process is able to make progress, they are getting this illusion that they have a private CPU of there, because they can make progress, they can execute on the CPU. So by time sharing the CPU, the operating system virtualizes it. It takes a single physical resource and kind of creates multiple virtual resources out of it, right? So this is a concept, right? Basically, time sharing gives the illusion of a private CPU for each of the processes, right? A consequence of time sharing is that now we as a user do not have to worry about the number of CPUs in the system, right? Like, irrespective of the number of CPUs, we can launch a program, and when it starts running, it will become a process, right? And the operating system, whenever a new process is created in the system, it is the responsibility of the operating system now to allocate a chunk of the CPU time to the process, right? Whatever program that you launch, right? All of them will start running, and we know that a running program is a treated as a process by the operating system. And the operating system time shares the CPUs, the limited number of CPUs, among all the processes in the system. So whatever programs that you launch will become a process, and once it starts running, once it's a process, it's now up to the operating system. It's the responsibility of the operating system that it will guarantee some CPU time to your process, right? So you as a user do not have to worry whether there are enough CPUs in the system or not. You can just go ahead and launch your program. It will be a process, and the operating system will definitely guarantee, like, it will that your process will get some CPU time. It will execute. It will make progress, right? So you do not have to worry whether. So in the absence of time sharing, if there are limited number of CPUs, then you are kind of constrained by the number of processes that you can launch, right? When there is no time sharing. But since the operating system time shares the CPU, it allows us, it makes us capable to run way more number of programs than the number of CPUs. And this is what makes the system easy to use. This is the fundamental goal, right? We discussed that the fundamental goal of the operating system, there are two, right? One is to make the system easy to use, and the second is to ensure that the computer system is used in an efficient manner, right? So The important part about time sharing, the most fundamental benefit of time sharing is that the system becomes now easy to use, because you as a programmer, as a user, does not have to worry about the number of CPUs. You can just go ahead and launch your program. Once it becomes a process, once it starts running, the operating system guarantees that your process will get to execute on the CPU. It will get some fraction of the CPU time, right? So this makes the system very easy to use, and this is the overall goal of having processes and time sharing the CPU between these processes, so that the system becomes easy to use. You as a programmer don't have to worry when you're launching programs, right? So now we have developed a good understanding of time sharing. We discussed several points related to it. From the subsequent videos, we are going to understand how the operating system implements this mechanism in the system, right? So if you look carefully at time sharing, then there are two important pieces. The first part is the processes itself, right? Basically, the processes will be time sharing the CPU. So the first part of time sharing is the processes, and the second important piece in time sharing is how we switch the processes, right? How we allocate the CPU to different processes. So the first part is how to understand processes, which we have been doing until the previous topic. So the first, if you look at this module, the first four topics where we introduced the concept of processes, then we talked about address spaces, then we discussed about system calls, right? This was the previous four topics were about developing a good understanding of the processes, right? Now we have understood the first piece of this puzzle. The second piece, which is what we will be studying in the next two topics, basically this fifth and the sixth topic, is to understand how we can switch the processes, right? How we can like time share the CPU. First part was understanding the processes. The second part was understanding how we will be switching the processes on the CPU, right? So this and the next topic is about that, right? So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.